I would like to introduce our first speaker, Stefan Savage, who is a professor of computer science at UC San Diego, where Stefan has been doing work in evidence-based cybersecurity for a very long time, actually. When I first met Stefan, he was doing a lot of work on worm detection back in the era of big worms, and that segued through so many different spaces that he's become involved with in terms of cybercrime and analyzing cars and avionics and all sorts of other things. Stefan has more awards than you can shake a stick at, and so I won't list them all so as to avoid embarrassing him. But needless to say, and I will say the concluding line from his bio, which is that he's a fairly down-to-earth guy and only writes about himself in the third person when asked. I think you will enjoy his talk very much. I'm delighted to have him here. Stefan, I'll turn it over to you.
Thank you very much. Today I'm going to talk a little bit about how me and others who work in the field, at least the way that I do, try to use data in order to make cybersecurity a kind of a real boy discipline that is not just based on gut feeling. And so to provide a little bit of context, here's kind of the motivating 10,000 foot level thinking that goes behind quite a bit of my work. That we spend a ton of money on security today, but it is very much of the reactive variety, that there's a new problem, we have to keep up and come up with a new defense, or we have to change the way we have something configured. And there is very little sentiment that we understand that our expenditures are in fact being put out in a wise way that addresses the threats that we believe we have. And so the question really is, all right, so we have a limited number of dollars. We can't spend all of our money on cybersecurity. How much should we spend, and how, and on what? How should we reason about these kinds of things? And the unfortunate truth that really, I think, in the real world drives a lot of the problems we have in cybersecurity is that there is a fundamental information asymmetry in the way this game is set up. Attacks are easy to measure, defenses are hard to measure. So attackers, particularly those who are financially motivated, have extremely well-defined cost structures. So if you want to buy 1,000 compromised machines, the going rate is in the neighborhood of $100 for Western democracies, in the $5 or $10 in parts of Southeast Asia. If you want to buy accounts, it's $4 to $8 per 1,000 accounts. We have well understood business processes and business models where they know what their return on investment is. They know if they can get their malware to infect a few more things, or they can get their mail filtered a little less, or they can get into a larger organization to hit it up for ransomware. They have a sense of how much money they will make for getting better. This tends to create a positive cycle that causes attackers to get better and better in order to extract the revenue that's available. On the defensive side, we largely do not have the equivalent kinds of metrics. The most metric, to the extent that we have them, they tend to be process-oriented. Do you have the following mechanisms in place in your organization? So you take like the NIST framework and then you break it down into checkbox items. And so the consequence in the real world, and this is somewhat counterintuitive if you don't live in security, is that people selling security products do not compete on the security offered because it is not possible to compete on it. At least it's not possible to compete on it in a way that you can show that to your customers. So, that's not to say they don't try to make their products better. They all do. But we don't have a way to put that into a solid empirical framework where we can say this one is better than that one. Like how much better is Symantec than McAfee, and what are even the units of that? And so most of our investments are driven by some combination of intuition or compliance requirements that are placed on organizations by the state. All right. So much of what I do and the people that I work with is trying to put cybersecurity on an evidence-based footing, the same way that we've tried to do with healthcare, which is also messy. So people say, oh, cybersecurity is messy. Well, healthcare is also messy, and yet they managed to pull it off. All right. So the motivating question is, how can we make better security choices? And the answer that me and my colleagues have come up with is to have empirical data and measurements that focuses on outcomes the same way we do in healthcare. What is the relationship between intervention and outcome, whether or not there is a negative security event? And in this, you have to include both the technical measures, but also all of the extra technical issues, because in the real world, those extra technical issues, economic issues, social issues, human factors issues, are every bit as important as the technology. And this is one of the reasons why even if we get to a point where we are able to have proofs about the soundness of our software and everyone uses Rust and so forth, security problems will not go away. All right. So this talk is really, I'm going to illustrate some of the different ways that we have tried to do this through a set of examples. This is a larger set that I'm going to present because this is excerpted from a larger talk that Sean has seen previously, but I wanted to give you a flavor for the different ways that we try to analyze data in order to make positive changes in security outcome. All right, so one fairly simple notion is examining how we measure the strength of defenses. I put that up earlier as a challenge that we have in this field. And so how do you know how much better things are when you employ a defense? How would you what are the units for that? And so the example that I'm going to put up there is going to be CAPTCHA, but it could be all kinds of things, for example, on account sign up, like velocity filters, IP reputation, SMS challenges. How do you decide whether to employ one of those? How much better will it make it? And this is a place where there are no first principles. We do not have crisp ways of doing these things. And so companies historically have done it based on a sense from their CISO that it was a good idea or not. All right. So the approach that we took was to think about this economically from the standpoint of your adversary. So if you have a big enough target, what has happened is, because the internet enables infinite amounts of communication, is there emerges a retail market for defeating your defenses. And so you can value the security that your defenses offer as being part of what is built into the pricing for the service to defeat your defenses. All right, so a simple example is CAPTCHAs, which you're all familiar with. Originally, when Louis von Ahn came up with this, it was envisioned as a computer vision problem. In the real world, it is rarely a computer vision problem because it's not economical as a computer vision problem. And so what happens in practice, the way that people who are trying to do bulk account registration to abuse Google or Yahoo or whoever, is that it is outsourced to humans. All right. And so the retail rate to solve CAPTCHAs is somewhere between 50 cents and $1 per 1,000 CAPTCHAs solved. All right. And so on demand at any point in time, there are roughly 1,000 workers available who just are solving CAPTCHAs all day long. You might ask, well, how do I know that this is the case? And the answer is, and this is a classic part of our methodology, is, pretend to be a criminal. So we signed up for basically every CAPTCHA solving service that we could find, both as a retail customer, and we signed up as a solver, as a laborer who wanted to provide work. And from this, we were able to establish how big the market is, how much load it could handle. We temporarily cornered the market on CAPTCHA solving to see at what point latency degraded and so forth. But from this, you can conclude this works quite well. It is quite efficient, and see how it has evolved to solve different markets. Now, you could look at this and say, well, this says that CAPTCHA is a failure, right? It takes 1/10 of a cent to defeat a CAPTCHA. How good is a defense if it only costs 1/10 of a cent to defeat it? And the answer is it's pretty good, because the right way to look at this kind of defense is that it is a filter to separate out your potential attackers who have business models that are not robust enough that they can return 1/10 of a cent per compromised account, which is actually fairly difficult. So it is basically a high pass filter that cuts out all the ankle biters, which is the majority of people, and leaves you with the people who have high value scams. Right? It does not solve the problem. It filters the problem for you. Now, what is this good for? Well, one thing it's good for is you can then go and when you are adding things to your defenses or changing your defenses, you can evaluate how effective your change was or your addition was by looking at the change in the underground market price to address this. And so some of our early work here was done with Google. So circa 2012, the going rate for about 1,000 webmail accounts was in the $8 to $20 range. It didn't matter if it was Hotmail or Google or whatever. So Google then added phone verification, which was SMS challenge primarily, to its account enrollment. So you would sign up for an account, but then you had to provide a phone number. And then the question is, how effective is that? And what you could tell then, and this is just a singular example, we looked at pretty much all the different sellers that we could find, was that there was an order of magnitude increase in the price. PVA here stands for phone verified account, for getting a Gmail account at the time versus a Hotmail account, which did not have phone verification. And that filter, in effect, was increasing the cost structure for criminals by a factor of 10. And so that's a direct measurement of how effective this is, at least against one large class of adversaries. All right. And I'm happy to take questions at any time if people have any. I'm going to go through some of these examples, and hopefully these are the kinds of things that get people thinking about different, more creative ways to think about measuring security. So another effort that we focused on was trying to understand, again, from the standpoint of thinking of the attacker from their standpoint and their economic self-interest, is focusing on the bottlenecks that they have. And so since to this day, for most attacks, the driver is financial reward, we went and said, look, all right, there's all of these different kinds of activity out there. However, so in this pyramid that I've shown here, we have different ways that actual scams are monetized. On the left-hand side, we have what at the top left is what I would call advertising. Things like, Viagra spam and so forth. On the upper right-hand corner is things like bank credentials theft. And a lot of this other stuff, whether it's the Trojans or the botnets or exploit kits, all that, those are all cost centers. So these are all things, none of them make money. They're things that criminals need to expend money on in order to enable them to get to one of these places at the top from which they can extract revenue. So this is a study back in I don't know, maybe a decade ago now. We went and looked at this in the context of email spam. And we said, let's look at all of the pieces that are required for someone to make money on an email spam message. So the part that we primarily focus on traditionally is the botnet and getting it in your inbox and the fight with spam filters and so forth. And so for this particular piece of mail, it comes in and, whether or not it gets into your inbox is the question. Then the next issue, is you have to be able to click on this link. And so that means someone needs to register that domain. This was a registrar in Russia called reg.ru. There has to be a DNS server. And for this particular email, there was a DNS server in China that points back to a web server, which was actually a proxy located in Brazil, that in turn reaches back to this criminal affiliate program. You can think of this a little bit like multi-level marketing, who actually handles the shopping cart and payment processing aspect. They in turn interact with a Azerbaijani bank in Baku who handles the Visa payment, and then contracts with a third-party dropshipper out of India. So all of these different lines here represent different commercial relationships, some of which are knowing and complicit, and other of which are just offering services. But any one of them, if that service was not able to be rendered, would have prevented this email from being monetized. All right. And so the question is, where are the bottlenecks? Where are the places where if you went in and you snipped one of these lines, that it would do the most damage to the overall economics of this enterprise? And we again explored this empirically by being the most gullible user on the planet. So we got a lot of very big companies to send us all their spam feeds. We had a rack full of servers that crawled every piece of spam they got, visited every URL. We did a lot of clustering, which is a whole topic in and of itself. And then we were able to cluster them to the different criminal programs behind them. And then we made purchases from all of them as well. And so we had a special relationship with the bank. So we were able to get full transaction data saying, where did the money go? And then take receipt and see where did we get stuff from and was it actually the drug and so forth. And so we bought a lot of stuff. That's what we did. And the end result was actually was fairly interesting. One is that most of the online resources, domain names, hosting facilities, botnets, et cetera, had extremely low replacement costs. So you could knock them out and the impact would be very short term and would be modest with respect to their overall profitability. The exception actually were the banks that they used in order to accept Visa payment. And there's a set of complicated reasons that we didn't understand at the time, but I do now, that I'd be happy to talk about if people are curious, that meant that there were actually substantial losses, sometimes in the millions of dollars, if these banks got shut down for abuse. And that there were only a handful of banks that did this across the entire world. And so we spent a bunch of time working with brands and folks in the White House and Visa and MasterCard to do this undercover purchase regime where you track which bank is accepting the money and then work with Visa or MasterCard to take down the bank account. And so I'm just going to show you a couple examples. This was our pilot study done with Microsoft against those selling what was called OEM software, but basically counterfeit Microsoft software for money online. And so in 2011, Microsoft started merchant complaints driven on the data that we gave them. These are comments from inside, in this particular case, it's an affiliate program called Software Sellers that we had also joined so that we, the moral equivalent of battle damage assessment, so we could figure out what was going on. This translates to, dear advertisers, we're having trouble with our bank and our accounts are suddenly frozen. We have to stop accepting traffic like this. And then shortly thereafter, OEM Pay says, our bank has stopped working. We have to close our affiliate program. And then my favorite, in early 2012, very Russian and very poetic, the sun is setting on the OEM era. And this was actually an incredibly effective takedown, as I'll summarize later. Basically, it became impossible for 18 months for you to buy counterfeit Microsoft software. It was more effective than anything that they had ever done. Online. And there's a similar story in pharmaceuticals. Without going into as much detail, this is the summary of someone who's running a criminal program to all of its members. All right, so highly effective, cuts down, basically people are no longer able to sell counterfeit Microsoft software. Half of the counterfeit pharmaceutical companies come out. There's now an industry-led program that does this full time. And all of the European banks depart the market because it becomes too hot. And it's now there's a handful of banks in China and Azerbaijan who are still here. But this remains because it does not have a clear replacement. The average US consumer is not using Bitcoin to buy their Viagra. It is the bottleneck. And the way to figure out that it was the bottleneck required doing all of these measurements. There was no other way to figure that out. All right. Then the next topic I wanted to talk about would be very different, a little bit more machine learning-y, which seems like it's been the thread in this workshop, is dealing with vulnerabilities. So, we have thousands of new vulnerabilities disclosed every year. Every enterprise has a large number of those that affect software that they run. And so the question for system administrators is how to triage. Which vulnerabilities do you address first? Which do you patch and which do you patch later? And the way you'd like to answer is which are the most important ones? Which are the ones that if I don't patch them, my company is going to get owned? And the other ones are the ones that are less important and I can wait. And the industry standard is something called the Common Vulnerability Scoring System. It was developed by industry in partnership with FIRST, which is the Organization of Incident First Responders. It's now in version 3.1. It is the de facto standard. It is what everybody uses, excepting maybe Microsoft, who has their own thing, in order to come up with a number that says how bad a vulnerability is. And I'm not going to go through this in detail, but they have a whole, you can read it online, complex structure for how you come up with a number for how bad a vulnerability is. And there's the how bad is the vulnerability itself. There's this temporal component, and then I'm going to ignore the environment. I'm just going to focus really on the first one, which has two components. One is how hard is it to exploit this vulnerability? And then how bad is the impact if it is exploited? And I'm going to focus on exploitability because that's the one that says, is it likely to be exploited? And this is what this looks like circa version 3.0. In 3.1, the numbers change, but it's pretty much the same thing. You go and say, how hard, what do you have to do to access it? Does it require local access? Okay, then it's 0.395. Then there's this arbitrary notion of high, medium, and low access complexity and similar things. And then you multiply these together and you put them into this larger formula that's put together by experts, and then you get the score. That's the answer. That is how CVSS is calculated. And it is extremely well considered how they put it together. However, it is a static metric designed by experts at a point in time. And so we found ourselves saying, well, what if instead we just built a learning model that looked at when vulnerabilities get disclosed, when they are exploited in the wild, and then use that as the supervision to build a model. And the result was like a really, really stupid machine learning model, because we're not machine learning people fundamentally, totally dominates CVSS as far as its predictive value, right? So the simple model can get you 85% accuracy on, is this going to be exploited in the next 2 weeks, for example? And others have done much better since, because as I said, this was not a strength of ours. So this is a place where you can take the data and say, well, I just need to figure out the right question to ask in order to be relevant for this concrete security question. All right, and then the last thing I'm going to talk about is an ongoing project. This is kind of a bit of pilot work. And this really, again, the first two parts focused on things from the standpoint of the attacker. These last two have focused on from the standpoint of the defender. And we have a ton of kind of received wisdom about what our best practices are. So we should run antivirus and update your stuff, patch quickly and don't go to risky sites and use a password manager, all this kind of stuff. But the fact of the matter is there is no data justifying this wisdom. Like, we do not know that it makes it that you are safer if you use antivirus. We just feel that it must be true. But no one actually goes and checks to see if that is the case. And it would be preferable instead to have data. So there's all these various cyber hygiene practices and say, all right, how do these correlate with outcomes? Like, if you run antivirus, compare the using antivirus group to the non-antivirus group. Is there a correlation with whether or not your machine gets owned? All right, and then later work on causality, because causality is quite tricky in this space. But even getting correlation is not something we have today. And the reason we don't is that it's hard to get. It's hard to get this data. And bad things are, as much as we read about them in the paper all the time, they are rare. Most of the stuff going on your computer is good. And so in order to actually get statistically significant samples, you need really large scale. And so there are very few organizations that are set up to do this. All right. So we started this project at UCSD called the Cyber Hygiene Project to do large scale feature collection for exactly this kind of work. And basically the way it works is we collect a ton of passive data, originally from the residential part of campus and now from other parts of campus, and use it to basically come up with feature labels for all of the activity that is going on in the network. We then go and take all of that and combine it with outcome data about machines that get compromised from our IT support group. So things that they have to deal with, or IDS alerts that show that a machine is anything that would cause us to shut down a machine and fix it will get put in this. And then we can correlate those outcomes back to, well, is there something different about the activity of the machine that was compromised versus other machines that are otherwise similar? And so we collect a ton of different features of these, actually a lot more than this, but of the kinds of received wisdom, like, do you run antivirus and what kind, and what's your operating system, and do you have a password manager, and what kinds of applications do you run, and what kinds of content gets visited, and so forth. And so I'm just going to highlight a couple kind of early results to show some of the complexity in looking at this kind of data, but all the more reason why we should be doing it. So browser updates is one where we say, look, everyone should be keeping their browser up to date. It's the key way we interact with the internet. And they update it with security patches all the time. You should update. And you find this very unintuitive result, which is that the mean time for machines that are not compromised to update is, for both Chrome and Firefox, is longer than for the mean time for devices that are compromised. So in other words, compromised devices seemingly update more quickly than clean devices. Now, I'm not going to suggest to you that that means that you shouldn't update your browser so that you can be more secure. This is why this is complex. And so if you dig into the data more, what you find out is the explanation for this result is that compromised devices update much more quickly after they've been compromised, because people find out they've been compromised, and then the first thing they do is they say, oh, I need to be much better about my hygiene. And so this is one of the pitfalls of correlation not standing in for causation. So in fact, if you look at the mean for the time before compromise, in fact, these machines are the same as otherwise. One that is more significant is there are certain software systems that if you run them, if you have that feature in your past, that you are significantly more likely to end up compromised. And so, the right-hand side here that shows the ratio of the machines that have this feature to the ones that don't. And what you find is if you are running peer-to-peer applications or use Adobe Air or Thunderbird, that you are substantially, 2 to 8 times more likely to end up being compromised. Now, this is not causal. Like, use Tor. It's not that Tor is compromising you. All right. And this is something that has to be teased apart, but it is more likely that's what's going on is that people are using Tor to access resources that involve greater risk. But this is exactly the kind of work that one has to do to kind of tease this stuff apart. All right, so kind of in summary, I'd say, like, traditionally we've said, well, we can't really measure security. And I would argue that that's a cop-out. It is hard to measure security. And also, like, security is not one thing. But there are really important security questions that we can measure or measure aspects of at a point in time, or measure the change in, if we're creative about doing it. And so getting better empirical data ultimately should put us in a position of being able to make better concrete security decisions. And as a side, we are always looking for partners who are interested in this and have good data. And so with that, I am done. And I'm happy to take questions or just advance to the next speaker.
Thanks, Stefan. I thought maybe we would just do one, possibly 2 questions now, and then move on to Mayank. Any questions from the audience at this point? I actually have one, Stefan. So I want to summarize a couple of things. So you've done a lot of work that has broad benefit. I'm thinking a lot of the internet cybercrime work to identify the merchant banks and so on, and the work with vulnerability scoring systems and so on that I think a lot of people can make use of. I think you've also demonstrated that security is measurable, albeit, as you point out, hard. The broad question is, other than partnering with your team and supplying data for you guys to analyze, how does measurable security scale? How do for example, the work that you did on analyzing cause and effect on the UCSD campus. How do other companies do similar things to gain insight into their own organizations?
I'd say it's really hard, because very few people have the budget. I know this because we effectively are this team for our IT folks, and they love having someone who will just sit there and dig through their data. They could not afford it. I think that it's a misplaced savings, because absent going and looking through their data, there is no, they're just doing the things that other people do. It's more of a CYA than anything else. I think this is the kind of thing that will take more of an institutional push. That they need more guidance, and also, frankly, support. There needs to be companies that do this kind of stuff, and not just a handful of academics. But I think someone is going to need to require it to make that happen. I think the closest thing that you see right now, which I don't think is equivalent, but is starting to move in the right direction at least, is you do find third-party companies who are providing risk scoring to the insurance industry for underwriting cybersecurity policies. Mm-hmm. And they are data-driven. There are now a number of these companies that will go and measure things. They're mostly outside the firewall, so they're not really looking what's going on in your organization, but it's a step in the right direction. It's kind of trying to use data to try to talk about risk in a way that guides behavior. I think the other thing that would be great is if more academics got involved in what I would call the kind of work that it's kind of ugly, but involves the real security problems. Go to your IT people and ask them, or the companies you work with, what are your day-to-day, honest-to-God security problems? And at first, they are going to be so much less sexy than using whatever homomorphic encryption in order to exchange data in such and such a way. But I guarantee you there are some fascinating problems in there that they have. And just there are not very many people in academia who are actually working on the ugly, how do you actually manage security in real organizations problems.
Fascinating. Yeah, no, thank you for that, Stefan. Those are great thoughts. And the insurance one, I think, is particularly interesting. That seems like one that's only going to expand. Do you think that there's also an impending parallel to the way that this has worked in healthcare? I mean, there's an actual agency that does healthcare quality research, ARC, right? Do you think that's on the horizon for us in cybersecurity?
I think we're a ways away. I think we're not. Look, it took healthcare a while to get there, and it was not welcomed originally. And I think in effect, what really made it happen was the advent of managed care, because it was not a thing that individual doctors or practices were going to do on themselves. But suddenly, when there was an opportunity when the subset of evidence-based medicine that was going to keep people from spending as much on insured patients, it became clear, then you have, the managed care companies and the Kaisers and so forth get really serious about analytics and force their institutions to do that. I don't think we have yet an equivalent kind of mechanism for kind of broader IT use.
Got it. Well, and maybe, as you say, the driver will be insurance. I guess we'll see where that goes. Well, thank you so much, Stefan. We'll stick around. And if there's more questions for Stefan, there'll be an opportunity at the end of all of this to ask. Please feel free to save them up or put them in the chat, and I'll collect them and ask them at the end as well.